So in the previous video, we gave two different definitions for what you could use to identify something as an acid or a base. There was the Arrhenius definition, but then there was also the Bronsted-Lowry. And I first want to start off in this video by pointing out that an acid or a base could be identified by more than one of those definitions. All right. So for example, if I were to show this reaction right here and just say what role is this chemical right here acting as in this reaction? All right. Well, one person might look at this and say, well, it's a hydrogen-containing compound, and when it reacts with water, it makes H3O+. And by that definition, and if you look at it that way, you could identify it as being an acid by the Arrhenius definition. All right. But another way that you could look at this is just pretend that water is just a normal chemical, and in the process of doing this, this substance right here is donating an H+ to water. All right, notice that when this water goes from being H2O to H3O+, so it's accepting an H+, but this thing is going from HNO3 to NO3-. All right, so it's losing an H+. All right, so since this thing is donating an H+, that would make it an acid by the Bronsted-Lowry definition. But notice, either way you look at it, it still would be identified as an acid. All right. So here's the thing: if what we're saying is that to identify something as an acid or a base, we have to actually see it, the role that it's playing in a specific reaction. Well, why do we commonly call certain things acids and other things bases? All right, and that has to do with a more common definition of acids and bases, and that is, how would that chemical react with water? All right, water is as you know, a very, very common chemical in our environment. Life depends on water, and essentially, if that chemical would react as an acid when reacting with water, then we commonly call it an acid. All right, so for example, if we took hydrochloric acid and we reacted it with water, this is what would happen. All right. So if you look at the role that this thing would act as with water, you can see that it makes H3O+. All right. Another way that you could look at it is you could say that it donates a hydrogen to water, and that means it's acting as an acid with water. So since it acts as an acid with water, we commonly refer to it as an acid. All right. So when you're doing this, you would be making the water acidic when you add this acid to water. And we're going to talk about what it means for water to be acidic in basic in just a little bit. All right. In contrast, if we took this chemical right here, which is commonly referred to as ammonia, and you added it to water, what it would do is it would accept an H+ from water. All right. That would make hydroxide when the water loses that H+. All right, and when this thing accepts that H+, it becomes NH4+. All right, so because of the role that it would partake in this reaction with water, since it acts as a base with water, we commonly refer to this as being a base. All right, and if you were to add this to water, you would be making the water basic when you did that. All right, so in other words, if you act like an acid with water, you're commonly considered an acid. If you act like a base with water, you're commonly considered a base. All right. One thing, and we covered this a little bit earlier this year, is that you can tell a lot of times you can tell whether something is an acid or a base from its formula. All right. And recall that the formula of an acid, generally, if the formula starts with a hydrogen and it ends with, you can either say a nonmetal, but generally that means a halogen, or if it ends in a polyatomic ion, it's most likely an acid. All right. So, for example, if you had HCl, notice that it begins with a hydrogen and it ends with a halogen. That's hydrochloric acid. All right. HF is hydrofluoric acid. All right. But also it could end in a polyatomic ion. Notice that SO4 ends in sulfate. All right. And we had that thing where, remember the at-ic, and you just say it in your head as 8-ic. All right. If it's a polyatomic ion that ends in 8, sulfate, then you change the suffix to ic. So sulfate becomes sulfuric, all right, and then you just put the word acid after it. All right, this is nitrate, so that becomes nitric acid, all right. And the general properties of acids is that they tend to taste sour, all right, although I would not, it's considered unsafe to identify things, chemicals as taste. A long time ago, this was actually fairly common for people to identify chemicals by taste, but it's not really done anymore. All right, we're going to be talking about pH indicators in a little bit, which is the more commonly accepted way to do this. All right. Another property about acids is that they tend to be electrolytes, all right, in aqueous solution. All right, so if you take an acid and you add it to water, you increase the amount that water would conduct electricity. All right. But acids also tend to react with metals to give off hydrogen gas. All right. So as far as the formulas for bases, the chemical either starts with a metal or ammonium and ends with either hydroxide, which is OH minus, carbonate, which is CO3, all right, or hydrogen carbonate, all right. So examples, so these would be the polyatomic ions. Remember that when they're in the formulas with the metal atoms, all right, so hydroxide by itself has got a minus charge, but when it's in a formula with sodium with that Na plus, you don't show the charges in the overall formula, all right. So sodium hydroxide, calcium carbonate, potassium hydrogen carbonate, these would be a couple of examples of formulas that would be bases, all right. In terms of their general properties, they tend to taste bitter. They also tend to feel slippery if you have them between your fingers, all right? I'll come back to that in just one second. And just like acids, they tend to act like electrolytes if you dissolve them in water, all right? So let me come back to this slippery feel, all right? There's kind of an interesting reason that these feel slippery. In fact, if you're wearing latex gloves, and you were to take a base, a basic solution and feel it in your fingers, it doesn't really feel slippery, all right? But if you're just with your bare hands, if you put it between your fingers, it does feel slippery. It kind of feels like soapy water, all right? And the reason for that is that the base is actually going under a chemical reaction with some of the fat molecules in your fingers, and it's actually making literally little bits of soap molecules from the reaction of the hydroxide ions and the fat molecules in your skin. All right, so it's literally making a very small amount of soapy water between your fingers, and that's why it feels slippery. All right, it feels just like soapy water because you're literally making a little bit of soap from the chemical in the base and the fat that is in your skin molecules. All right. That is, if you know anything about soap making, that is the way that they traditionally make soap. They take a fat molecule and they react it with sodium hydroxide to make soap. All right. So acidic and basic solutions.